in this session, I'd like to welcome our panelists here. We have moderator, Dr. Vikram Rao, who is from the Research Triangle Initiative. So he's here to take us through a scenario analysis of what it means to have PV dominated grid and what are the things that we need to take care of. In this discussion, he's joined by Dr. Preeti Agalyan from the Department of Chemical Engineering, who has a Center of Excellence or Research Initiative on underground coal gasification. We have Dr. Krishna Vasudevan, Professor Krishna Vasudevan from the Department of Electrical Engineering, who is working on research initiatives related to microgrids and related technologies. We have Professor Ashok Junjunwala here, who is leading the 100% RE effort. On the Zoom, we have Dr. Mani, who has a Center of Excellence initiative, research initiative on solar-based cold storage and desalination. We also have Professor Muruganandam, who is leading the initiative on advanced gas turbines, which can probably handle hydrogen and other fuels. Be shortly joined by Professor Arvind Kumar Chandran, who has this initiative on electrochemical conversion systems and photon electrochemical conversion systems. So this forms some of the main centers of excellence, of research excellence at IIT Madras as part of the Energy Consortium.
So let me add to the introduction that Satya gave. Initially, what we thought was we would do this panel. So these are the PIs of the 7 clusters. And initially the thought was to have each of them speak to their research. So I thought that was pretty boring. Now, the research is great, but I thought just talking about research is boring. So some of us, Preeti and Satya, and I decided to do this, which is create a scenario. Now, scenario is not a prediction. It is just one, it's a scenario. and it is used for predicting, but in this case, it's being used for just one thing, what I call grist for the discussion mill, okay? So it is just a way for us to discuss. And I picked solar PV, solar photovoltaic, because it turns out that when we discuss this scenario, it pretty much encompasses what the faculty do here. There are some gaps, but we'll worry about that. So let me just quickly walk you through for the next 5 minutes with, and I was going to use this on the screen, but it turns out the dot is not that big. But so I'll just walk through with words. Look in the middle, which says solar PV. So that is the middle. And then to the bottom right is all how the conventional world looks at solar photovoltaic, which is how to produce it, how to distribute it, and then how to use it. Actually, I might get up here and show you on the screen, let's say. So this part is here. So from solar PV, it can go to the national grid, or since many of you know, solar is naturally distributed. We, in our wisdom, tend to aggregate it into hundreds of megawatts, and you don't need to do that. So in a village setting, for example, you could have solar all in your home. Maybe you've seen that. So so the distributed generation is one entire sector, and within the distributed generation, there would be microgrids, and then there would be 2 legs. One is AC architecture and DC architecture. And Professor Junjunwala and others have done a lot in this area, and we'll get into it. But the point is, then the other part is the national grid, and then we look at desalination, which is some work that's being done here and so forth. So this whole lower right is what people in general think that governments think, and that governments have been encouraging with subsidies and so forth, is the lower right. What a lot of folks don't appreciate is that the sun kind of refuses to shine at night, and then there are rainy days, monsoons particularly. And so this whole left part here is managing interruptions. And interruptions can be a couple of types. One is, there's a classic 4 to 6 hours in the evening that people talk about, and because there's a lot of usage, but there's no sunlight, not enough. And so that is usually done with electrochemical storage, batteries. But there's some work going on, as Ashok pointed out earlier, Professor Ashok pointed out earlier, about batteries that might even give you longer term storage. But in any case, Electrochemical is one whole sector. Then other innovative storage, such as compressed fluids, air included. Air is a fluid, by the way. Engineers know that. And then when we look at managing interruption, we go to the whole top right. Now, this is the part that gets a little bit into what Ashok Krishna pointed out, which is that we're not going to walk away from fossil fuel in a hurry. But what can we do? Okay. And the reason we can't walk away from fossil fuel in a hurry is that today, 90+% of the longer term interruption management is done with natural gas or some other fossil fuel. It's just the nature of the beast. It is what it is. Now, we've got to learn to get away from it, but that is what it is. So for the foreseeable future, we're going to have to deal with it. Now, we're going to discuss some innovative ways to deal with it. And that's all right. I mean, the obvious one is LNG imports, the worst thing you can do, especially these days when the prices are extremely high. And then whatever you do to combust fuel, you want to catch the carbon and use it. But then this whole other right is an India context. Now, the India context doesn't make it, it's not a world context. It is. It just depends on where in the world you are. And where in the world you are will determine which of these matter. So, for example, when I call it domestic methane, it could be methane hydrates, which is in ocean beds. Or it could be coal-based, and coal-based go. By the way, this thing is something called a mind map. Okay, it's busy as all get out, but it covers the ground of externalities. It covers the ground of dependencies, what that oval needs to survive, or what it produces. So that's what this mind map is doing. So take coal, for example, which for quite a while this country and many other countries are simply not going to be able to do without. But instead of just combusting it, you could do this. You could gasify it. Gasifying is where you combust in a reducing atmosphere, okay, where there's not a lot of oxygen, oxygen starved, let's call it. And you could do it ex situ, which means above ground, or in situ, which is underground coal gasification, and so on. And then you produce something called syngas. Syngas is called synthesis gas. It's known as syngas. And from syngas, you can make anything. All plastics pretty much are made from syngas or naphtha. So and from syngas here, I've got not making anything, just making specific things. I've got making methanol, which then can go back and be combusted. I've got it where I will shift react it to hydrogen. Okay, so some of this is all chemie stuff, just deal with it. Okay, you do something which then shifts it to hydrogen and CO2, but you get a lot of CO2 production, then you've got to do something with CO2. And then you've got other things. From syngas, then when the hydrogen can then be transported directly and burned directly, not one of my favorite things. You want to do other things with it, such as ammonia. So if you do synthesize ammonia, and if the hydrogen didn't come that route, but came from this route, electrolysis, this is called green hydrogen, it'll be green ammonia. And so you get the picture. This whole upper right is kind of a consequence of the reality that every time you put, it's kind of an inconvenient reality to a lot of folks. Every time you put up something in solar, you are creating demand for a fossil fuel. And if you don't want fossil fuel, you better be doing some of these. Okay, so this is it. So now, what are we going to do? What we going to ask these folks to do? They've all received this earlier, so they've had a chance to. So there's no excuse for not having prepped it. They've all been asked to speak to how how their research fits in this. And when we're done with this, actually, we'll handle it. I'll handle it depending on what they say, and then we'll be left with gaps. And then we will have a discussion. So this is an immersive discussion. Part of the purpose is to say how their research fits in this, but the other part of it is for us to all together sort of figure out how this problem is going to get solved. And what is the problem? The problem is you want to go gangbusters on renewables, cool, but understand that it's intermittent. There's no renewable that's not intermittent other than one. And we're not going to discuss that today, although it's one of my favorites. And we won't be discussing it today. Then why the hell am I discussing, I guess? Or anyway, there it is. It's geothermal. And geothermal is the only 24/7 renewable. But as I said, we won't be discussing it today, except I sort of alluded to it. All right, so here we go. And what we're going to do is he's going to be last because he's different. And we will go from left to right, and then we'll go to the virtual people, and then he'll be handled differently. Okay, let's go. You get 5 to 7 minutes, as you know. Okay, all right.
So I'm Aravind. I'm a faculty in chemical engineering. I work predominantly on solar energy conversion and storage. And by looking at this plot, whichever that has been introduced to you, there are a lot of things that I'm quite excited about. I really wanted to jump and talk about everything, but I'm going to vouch for a few things which I feel that I prioritize and which I think we'll have to probably focus on. And not all of us feel that whatever I'm doing is going to be the best, but I'm going to really say why what I'm doing is best and what, as an institute at IIT Madras and as a country and as a world, I think we'll have to focus on to go to the net zero carbon. So solar energy is one of the primary energy sources that's available across the country, across the world. But the only problem with it is it varies quite a lot. In our group, we did a very quick analysis of solar energy data, NASA's and MNRE data, all the way that's available from 2007 to 2014. And we found out that, for example, you take Jammu and Kashmir. During the January time, you roughly get somewhere around 2 kilowatt hour per meter square per day. That's a theoretical maximum. And whereas in June and July, the same state gets somewhere around 5.5 to 6 kilowatt hour. So that's like variation during the, like from month to month, from January all the way when you run across to the July, and then eventually to the December, it will come down. And within a day, eventually you will also have some other issues. Within a day, you will also see during the morning time, it's quite low. And then as you go towards the noon, it's quite high, and then it eventually comes down. And some of our prestigious speakers earlier this session, including Professor Ashok Junjunwala, mentioned that the wind is available only for 4 months on average a year, and the rest we do not have. So essentially, the energy storage is of prime importance. That's something we cannot avoid. I think we really have to go and do a good energy storage system. And there are a few things we believe in. One is direct solar water splitting. That is, we'll have to split water using a single system where water is converted into hydrogen and oxygen. This technology is something that's very well known, like for the past 50 years. Thing is that, as I'm going to talk in terms of like an academician now, we have not solved the problem at all. We have been talking about solar water splitting, but we never made it to the commercial reality because we never took the actual challenge of the reality. Rather, we took a kind of academic challenge. I'll put it this way. Most of the academicians live in our own world, and that's very true in India, and that's like highly dominated in India. The academic world is something very much unrealistic. Luckily at IIT Madras, that proportion is pretty low. So whenever we do this direct solar water splitting, we talk about like it's going to come to the commercial reality. I myself wrote some proposals on that, saying that it's going to be commercial reality. But the problem is when you put those kind of solar water splitting setup on the rooftop, you will have to pump water across the entire solar panels, across the, like that solar water splitting setup, literally several meter by several meters, several kilometer square areas. And they have to collect the gases across all the region. It's not going to be like commercially viable. Now, I'm going to come down to the next point. Before that, I'll also introduce the efficiency of these solar panels, solar photoelectrochemical setups are around 1%. And we have to seriously do something about it. I think it's an open invitation and a challenge that includes me, that we'll have to seriously work on this kind of like realistic challenge so that I can bring that photoelectrochemical setup where I can split the water directly on the rooftop and generate hydrogen. But then we cannot wait until we solve this photoelectrochemical system and then move on to the green hydrogen. By then it will be too late to solve the climate change. So can I bring in the existing systems and try to couple them together? Although it might not be an optimal and low cost system, but there is something that's available already. Let's say solar panels. At the moment, they are roughly around 20% efficiency, the good ones. And we have electrolyzers, which are fairly nice. And they are operating somewhere around 70 to 80% efficiency. Imagine I take 20% from solar panel efficiency, and I have 80% efficiency in the electrolyzer. light to hydrogen. Electrolyzers are just a device that generates hydrogen oxygen. That's something all of us are aware of. End-to-end efficiency is somewhere around, end-to-end, I mean, light to the hydrogen is somewhere around 13 to 14%, which is far higher than the direct solar water splitting that academicians are very proud of, in fact. So that is the reality. When I said there is a gap between the reality and then the academicians' reality is 1% and 13%. And I think we should really go on to this solar panel electrolyzer business, and then we'll have to see how to store that hydrogen at the next step. I think that's not the end of the problem. That's just the beginning of the problem. We get hydrogen. Now, like so far in all the industries, hydrogen is being like produced like locally, and then they're being used locally, except in few places. Now we'll have to take the hydrogen and then have to ship it to different locations. That there comes a new challenge actually. So at the Energy Summit, on top of the discussions we are going to have and we are having now, I think we all have to come together to work on all these things together, putting the solar panels plus the electrolyzer system together. And then on the other side, we have the hydrogen storage business that has to be also be addressed. And I'm going to introduce one more complexity to the solar panel and the electrolyzer itself. The fundamental issue, as I said at the beginning, like in Kashmir, January has 1 to 2 kilowatt hour during January. And in June and July, we have 4 to 5 kilowatt hour. So imagine you build a plant like for a certain amount of hydrogen or certain kilograms of hydrogen or tons of hydrogen per day, and you won't get the same thing in these 2 months. So essentially, networking the entire country is the only solution. Networking the entire country is the only solution. The thing is that you have to, the one thing that Professor Ashok mentioned, wheeling the energy from somewhere else and get the power to IIT Madras Research Park and make it 100% renewable. It exactly taxes the same point. We cannot install like let's say an electrolyzer of X megawatt and then operate it at 0.000 X megawatt. And then we lose on the investment. We lose on the total amount of cost per kilogram of hydrogen. So essentially, I want to conclude saying that we have technologies available. Solar panels are mature, electrolyzers are mature, and then we know how to connect both of them also. But then the solar energy availability itself is an issue from month to month, year to year, within a day. So we'll have to find a location-dependent energy storage system. The one that you develop for Chennai will definitely not be applicable when you stay in Delhi. You'll have to, because temperature-wise it's different, the solar energy availability is different. And so we will have to like literally come together and try to think this problem as not only a problem of IIT Madras Research Park, or Chennai, or Tamil Nadu, or India. It's a global problem, and everyone have to come together to find a local solution. And with that, I'll leave on to the panelists. Preeti, would like to continue.
Okay, before Preeti gets on there, let everyone think about one point that he made, and I'd like us to discuss that. Okay, one point that he made was, Arvind, not he, you're here, so I can refer to you by name, is that the variability from winter to summer means, and he made a flat statement, that means that we need to share with other regions of the country. I want us to dispute that statement, okay? Because then he's automatically saying that we need a grid in addition to distributed renewable energy. I'm not saying it's wrong. I'm just saying it's an interesting discussion, and I'd like us all to think about it. And I'm warning you that we will be discussing that. All right. And I'm going to give you also a statistic. Germany has 40% renewable on average. On any given day, it's 15. On any given day, it's 70. You see the problem with renewable. Okay, you're up, Preeti.
Okay, first of all, Arvind has already thrown me under the bus because he said we academics, especially at IIT Madras, or maybe not so much at IIT Madras, are very theoretical. But I will take that as feedback, and feedback, as we know, is the breakfast of champions. But I will talk now about some of the academic developments in our research labs, and I'll also place ourselves on this really beautiful mind map of Vikram's. So we are completely on the top half of this diagram. And I want to talk about 4 specific things that we have interest in and progress in, I would say, in our research initiative. First of all is on carbon capture and also the sequestration. Sequestration as a word is not mentioned over here, but it's there in the diagram in ocean storage, for example. So we have a large group that works on both of these aspects from a handful of viewpoints. We are looking at new ways to do this. First of all, we're looking at new materials for separating carbon dioxide from mixed feeds. And the second, also, we're looking at new and fun ways, I would say, of sequestering the carbon dioxide. My colleague Rajneesh is here. Significant developments in what is termed over here in this diagram. I promised you I'd place ourselves on the diagram, so I'm doing that very methodically as ocean storage, and specifically through CO2 hydrates, which is a very interesting, possibly not heard by anyone, too many of you, term, that is carbon dioxide hydrates. You've heard of, I think, methane hydrates possibly, but this is a little bit more cutting edge, and new. And so this is an area of focus for us, both from viewpoint of materials, new type of materials for membranes, and also new vistas in sequestration and storage. The next thing that third thing that we work on, I would call as carbon dioxide to what we are terming value-added chemicals. And despite all the disparagement by my colleague over here, this is also one area of contribution that Arvind has made. And he's looking at a photoelectrocatalyst-based method for converting the carbon dioxide to a chemical that has value. I think specifically formic acid is where we have some significant progress, and that's also there in the diagram in the top half. Aside from this, we're also looking at more traditional chemical engineering, bread and butter type of routes for CO2 to value-added chemicals. Sometimes we interpret it as CO2 directly going into these chemicals, and sometimes as CO2-rich syngas feeds going into different chemicals, including hydrocarbons, definitely methanol, which is also over here, and so on. And we are looking at catalysts that can help us do this type of activity efficiently and selectively. So obviously, chemical engineering academic has to throw out terms like this, but this is a focal area for us. I mentioned that there's a fourth area that we work on. That's more of a, I would say, a broad brush across all of these things, and which have been touched upon in this diagram. It seems like a good time to release a set of terms that I've been trying out in my head. We work on in situ, in operando, and in silico activities in our group. So all of these things, whether we look at your same old copper-based catalyst for converting CO2/CO2-rich syngas to value-added chemicals, or materials such as metal organic frameworks for examining carbon dioxide capture, efficient carbon dioxide capture. All of these things, what we want to, or what we plan to do in our group, little bit of progress already, of course, is to do these studies not separated from how they actually occur in the field and in practical application, but at conditions where it matters, not just in some really idealized lab type of conditions that typically academics would be accused of doing. In addition, we have a very large set of people that work on computational aspects. Now, computational aspects, of course, that's math modeling, simulations for reactors and so on, but with one difference in our case, that we look at all of these things, whether it is development of or better design of materials, optimization of reaction conditions and or reactor operating conditions, etc., from a viewpoint of a multi-scale model. So literally looking at from the level of a molecule all the way to an industrial sort of scale, I would say. So this type of multi-scale models, whether it be what is called computational catalysis or other more design relevant mathematical simulations, are part of our DNA definitely, and part of what we do. So that part is not there in the diagram, but it sort of brushes across many of the things that are especially in the top half of this mind map. So I would say that if we were going for a solar PV scenario, our contributions from our CCUS lab would be broadly in this type of region. So with that, hopefully I haven't taken more time. I'll pass it on to you, Vikram.
Okay, so let me similarly make a couple of comments for you to store. One is you mentioned the CO2 hydrates. I think it would be good for well, and I know you couldn't do it in your 5 to 7 allotted time, okay? But I think it would be good for a follow-on because that's interesting and it's different, people. And what is this? How are you going to do that? So I think it's good for you to address. If you don't, then I will. But moderator are not supposed to do that. So you should do it. And then Arvind had raised earlier that hydrogen doesn't transport something to the effect, and you can see, and you mentioned MOFs. Sorry, that's metal organic frameworks. It's a structure. Perhaps you can speak to how that plays to the hydrogen storage problem, and also we can also discuss how we can move hydrogen. You said it's difficult to move. It is difficult, but not impossible. So let's have that as a discussion. And I'm pointing this way, but obviously, Ashok, you can cover all of these areas. But I just want to give fair warning that we'll be discussing these points. Okay, you're on, Krishna.
Our area is mentioned from the distributed generation side. We are working in the area of microgrids. And we would like to look at the microgrids not just as electrical microgrids. Electrical microgrids is generally the most widely used and deployed means of that, but we would also like to look at it more broadly in terms of energy microgrids, where energy could be, in the form of heat itself, where we would like to have a grid formed for the distribution of heat energy also. That's the long-term vision. And as you know, these are essentially small grids which comprise of their own sources as well as loads. And the idea is that electrically, these grids can then operate along with the main utility grid, which is the electricity form. Or if the main utility grid is not available, then it can switch off from the main utility grid and operate in the so-called islanded mode. Right? So it's important that this grid operates both in the grid connected mode as well as islanded mode. And it's very interesting because if you have a grid that can operate that way, then we can establish this kind of a grid in areas that are fairly remote, which have no access to the main utility grid that we are all having now. And you all know as well that the grid is in an expansionist mode. So definitely the grid will reach there either tomorrow or day after a year later. So there will be a facility where even the remote areas may ultimately get linked up to the grid. But as what we are seeing today in those locations where such grid access has really happened, it has not happened to the extent which we are experiencing it here today, in the sense that the grid is not always available. And even when it is available, it's a fairly low quality grid that it's available. And therefore, it is essential that such grids be able to disconnect themselves from the utility grid and operate, all by themselves. And if this is going to happen, then we have another important aspect that's going to add to this, that in these locations, the energy sources that are going to be used need not be the ones that are, they are energy sources which are located at a distance. These remote locations can then use those energy sources that are abundant in that area, and then they can be enabled in order to handle and operate their own grid. So this essentially becomes a huge enabling aspect, and it will also enable the local economy to grow as you know, that energy is the essential feed for economic growth. So, in our activity, we are interested to look at the various technologies for energy sources, improve the technologies, and also we are looking at how these energy sources may be linked together to form an electrical grid. And we are also looking at, different uh, different varieties of locations across India. You may have these locations situated on a hilly area. It may be on a region that is flat. You may have locations where there are enough source by wind available. If you go to hilly areas, then it may be that you have sufficient amount of wind available. If you go to other areas which look like urban areas, for example, you don't have wind, but in urban areas you have another big aspect, which is urban waste, right? So if we can make use of urban waste and use that to get energy, it would be really good. And we are looking to see whether we can integrate that as well. So the idea is that we would like to look at the development of technologies for various varieties of sources. Of course, storage is going to be important, because without that, no independent grid can really operate. So we are going to look into that as well. So with all that, we are intending to sort of establish an exploratory microgrid inside IITM and look at how this is going to operate, look at the economics of it, look at the operational behavior of it, with the goal that if we are able to demonstrate this in IITM, then maybe with the help of industry and with the help of other support, we may be able to establish or install these ideas in other locations outside where energy demand is available. So you may ask that, are there not these systems that are already installed? So you will see, if you look around the world, that there is a fairly large installation of such systems with this kind of a goal, which is being deployed. But if you then look at how these systems are operating, you will see that the way the deployment happens is that they generally use one large source, energy source, which can be available on demand. And the other sources are only basically being used to offset it to some level, but not really to operate the grid itself. You look at the diesel electrics, that is the major source that is being used to deploy all across the world. And essentially, the entire world seems to be looking at the operation in a way similar to the normal utility grid. We are used to having the normal utility grid where you switch on an appliance, assuming that electricity is there. Right? And this operational behavior is what generally people seem to be looking for when they go for a distributed architecture. And if that has to happen, the energy has to be available on demand, and diesel generators are by now the most dominant form of energy source available. We would like to avoid it. We know that this is environmentally not useful, and therefore we would like to avoid use of diesel generators, which means that we are left with other forms of energy sources which are not available upon demand. And therefore, we now have an operational difficulty, which is what we want to address. That how do we then make use of multiple energy sources that may be available and operate the electricity grid itself? So this leads to an interesting aspect of first grid integration of several sources which may vary in different ways. So how much of energy storage would then be optimal for this? And how do you manage the energy distribution in the grid? If we look at this, we would also see that it may not be enough just to manage the sources of energy. We may also need to look at how to manage the loads. Because if everybody is going to demand that all my load should be up all the time, then we are effectively increasing the investment that goes into establishing an infrastructure, because you would definitely have to oversize them. So how do we optimally allocate the infrastructure? How do we select the sizing of all the equipment? And also, how do we do the aspect of looking at loads? How do you manage it? So this is a goal for our activity. There is one very important aspect to all this, because if we are going to install this kind of an infrastructure in a remote location, or even a location which does have access to grid but a fairly bad access to grid, we would depend upon the local community in order to handle and operate the entire system. We are saying that we want to make use of local energy sources which are available, which means that the local community involvement is very important. And we are interested in looking at looking at how to bring in this kind of involvement of the local industry there, or the local villages, right? If the installation that we are going to do, the technology we are going to give, is not applicable for them, and if they don't appreciate and use it, the whole thing will fall flat. And therefore, we are looking at attempting to see how we can involve them and incorporate their needs into the aspect of technology development. So apart from the hardware aspects of it, which we are hoping that it will lead to some deployments after this, we are interested in looking at the software aspects of it, which mean the operational, how to have the operational engine to attempt to operate these different sources, and whether this operational engine must be located in some central place or it can be distributed. All these aspects is what we are intending to look at in this Center of Excellence. With that, I will close and hand over.
Okay, so a couple of things that I think we'll follow up on. One is more in the area of question rather than a discussion, which is, well, interesting point you made that load leveling could be done from multiple sources of energy. I don't think many people are aware of that. I think would like to hear more examples of that on how that gets handled. I would say that's the principal question that I would raise, and because it might address in some ways what Arvind's point, the seasonality. Okay, if certain, so what I don't know, because I haven't really heard this concept before. Would it be that some of these are seasonally different from the others, and therefore seasonality is there? So I'm just throwing it out for think about it, more of a question than a discussion, and let's pick it up later. All right, let's go with. I'm being informal. Is Professor Mani?
My project is on desalination and cold storage system, which are all operated based on solar energy. So what we try to do is we collect the solar radiation using a thermal collectors. We produce the heated water. That heated water is flashed to produce a water vapor that is condensed by circulating the sea water. So what we intended to use here is we would like to use the inexhaustible sources of solar energy and the sea water for production of potable water. Depending upon the quality of the water which is available, the brackish water or the sea water, the appropriate desalination technologies can be used, like the multiple evaporator desalination system, multi-flash desalination system, reverse osmosis system, so on. This kind of system we have built at Vivekananda Kendra in Kanyakumari with the financial support from the Ministry of earth sciences on the seabed. You can Google and you can find out from the Google map the plant which is operating entirely based on solar energy. So the need of drinking water, the potable water for meeting out the villages need no emphasis for our country. So all the ancillaries are driven by means of collecting the solar energy by means of using PV panels. We have 30 minutes battery storage through inverter. We convert that into AC and drive all the ancillaries which are available in the market, procure it and couple the system with the desalination system. And we built with the capacity of 10,000 liters of water per day, and to meet out the drinking water requirement of about 5,000 people living in 5 villages like that. And the cost works out to be 43 paise per liter of water which is produced. In this plant, we are able to produce the quality of the water which will be of 2 to 3 ppm quality. We are able to produce it from the seawater. So what we would like to attempt is we wanted to use the heat transfer enhancement techniques to enhance the heat and mass transfer in the evaporator. Thereby, we would like to reduce the cost of the system, and also we would like to compact the system to reduce the cost as far as possible. And that is the first part of the project. And the preliminary studies, what we carried out by carrying out the laboratory measurements by using a metallic foams coated evaporator tubes, we observed that the heat transfer coefficient is enhanced by 3 times that of the normal tube heat transfer coefficient. And similarly, the mass transfer coefficient is enhanced by 2.5 times higher than the normal tubes. And that has been demonstrated, and we made a couple of publications in the international journals too. But at the cost of increasing the scaling effect. The scaling phenomena also we have studied for using a seawater. It is observed that if you run the desalination system with the heat transfer enhancement surfaces, the effectiveness of the ineffectiveness is reduced. Rather, the effectiveness is reduced by 20%. So that requires a prolonged study to come to a conclusion to arrive at the heat and mass transfer area that required be used. Thereby, we would like to compact the system and use it for desalination applications utilizing multiple evaporator desalination techniques. That is the first part of the project. The second part of the project is our country suffers with lack of cold storage systems, and also the cold storage systems available in the transport, which are all used for transporting the vegetables, fruits, and fish products, and so on. As per the Ministry of Food Processing Industries statistics report, which was reported during the year 2021, they told that as per 2015 data in our country, nearly about 90,000 crores of the food is getting food, or the food products are getting wasted. Hence, we would like to spend some time on improving the cold storage development also. If photovoltaic systems are available, if the power is produced and electricity is available, the conventional vapor compression refrigeration system can be used for a production of cold or cold storages. But we would like to concentrate from the thermodynamic point of view, if the heat is available. Using that heat, we would like to drive the vapor absorption refrigeration system or vapor jet refrigeration system to produce the cold. We have been working on these kind of heat-driven refrigeration systems. We would like to compact and try to develop a system to meet out the commercial requirement. As of now, in the industry, if the capacity of the cold storage or the refrigeration system is 50 tons and above, these absorption systems are commercially competitive comparing to conventional vapor compression refrigeration systems. So we would like to keep focusing on the absorption refrigeration system and compact it, try to reduce the cost of the system so that it can be adopted for small capacity systems like that. So this is what we focus on this. Based on the outcomes, we would like to involve the industries for commercialization of this kind of systems for meeting out the utility requirement of the public, especially in India, to meet out the drinking water requirement and the cold store requirement. Thank you.
Yeah. So, Professor Mani, a couple of things that we'll follow up on, not right away.
Okay.
But for you to think about. One is, what is the relative economics relative to reverse osmosis, particularly, and then the other question, and these are questions I have. Now, by the way, format-wise, any panelist can ask questions when we go into that phase. I'm just raising some right now for thinking before we do it.
Audibility is not there.
No, don't answer it now. I'm leaving it for us to discuss it later. And then the other question I have is, what is the applicability to highly saline water? So seawater is about 3.5%. Many saltwater aquifers are up around 10 or 15%. So I'm just throwing it out for you to park the thought, because in drought areas where fresh water is in short supply, the ability to access saline aquifers, which are plentiful. But I'm talking about areas that are not close to the ocean, of course. If you've got seawater, you've got nice 3.5% stuff, go for it. But I'm talking about other areas. So I just want to throw that out for us to discuss later. And then reminding the panelists, think about questions for to each other. Okay. So now, Professor Murgi.
I am heading this Center of Excellence for high efficiency, or in some sense high energy output gas turbine engines. Okay, basically we are thinking about moving away from liquid fuels to gaseous fuels. It could be liquefied natural gas, or maybe using hydrogen, or a mix of these two. That's the kind of direction we are going towards. The main change from liquid fuel to the gaseous fuel is that you may get higher temperatures if I add hydrogen, and that will correspond to having other issues, like only around 40% or 50% is converted to actual power output. Remaining is all going as heat. So we have to now worry about how to manage that heat. Otherwise, the engine will burn up. So those are all the directions in which we are working on. Actually, Professor Satya Sheshadri sitting there is actually working on that thermal management part of the problem. Krishna was there and is working on electrical management of that problem. Like that, I am working on the combustion side of the problem. I am going to come up with the designs that are going to be useful for hydrogen-based or hydrogen and hydrocarbon blend-based fuels. It's also going to be catering to sustainable aviation fuel. All that together. Okay, that's the basic idea. Since Vikram said that I can question others, I thought I'll just start it out with pointing towards Preeti. Basically, they are coming up with all these CO2 sequestration technologies, and I am thinking, okay, currently you are putting all these in ocean storage. There will be a time when that volume will be very, very high, and maybe that's going to cause an effect on the environment eventually. Currently, it's not. This is what Professor Vijayaraghavan was talking about at the beginning, right? It just comes back to that statement. So can we go the other direction of, say, mineralization, or say this in this coal fly ash? No, they just take it and use it for laying roads or making cements and such things. So like that, can we do something else instead of going and storing it in large volumes? Okay, in fact, our Chevron person was telling, like, they stored like millions of tons per year in there. That's a lot of volume. Somewhere it's going to cause trouble eventually. Maybe it's currently working for next 5 years, it will work. After that, it's going to cost trouble, right? That's one thing which we need to think about. Yeah, pointing to myself, I'm going to ask question. I don't know how to take this much hydrogen required for running an aircraft. Okay, the amount of hydrogen required to run the aircraft is going to be really, really huge. Something of the order of 300,000 kgs of hydrogen is required to run a 18-hour flight of 747. Okay, I just did this calculation back of the envelope. So it's of this order, and that's not easy to generate on an aircraft. So I think current technology, we will just develop it, okay, but without knowing where we are getting the hydrogen from. That's our center's current worry. Okay, but I believe that ammonia-based combustion might come up, or ammonia-based hydrogen production will come up, and based on that, we may use that in aircraft, and it can be stored in a simpler, easier, safer manner than storing hydrogen in an aircraft. Hydrogen in an aircraft is like a bomb. Okay? So we have to think about how to use it more and more safe. So that's the direction in which our center is supposed to work on. But currently, we are working on all these basic things about can this technology come? That's the other direction we had. Okay, so every person who was talking about, I'll ask the same question: will it have an environmental effect in the next 20 years? Okay, with that, I'll stop.
Okay, so you asked Preeti a question, which is fine. I'm flexible. I'm happy to go into. See, I didn't bring anything to write. You writing it down? Okay, all right. I'm trying to remember it all. But anyway, the question that was asked of Preeti, and it's a very interesting one because it actually goes in part to what I wanted her to get into detail, which is what is CO2 hydrate and how is it being sequestered in the ocean. And I think his point, well, you know what his point was, so you can address it. Okay, we will wait. All right. So now, Professor Ashok, okay, he'd asked me that he's not going to make a statement. He's talked already so much. So he said, I've spoken, you know what to ask me. You ask me something, I will answer. Something to that effect, okay? And so that's what I'm going to do. So I'm going to ask you, Professor Ashok, a couple of things. One is, and I know it used to be close to your heart. I don't know if it is now, but if you could point to one part of the mind map that didn't get covered, which is DC architecture. If you could give us a short exposition on DC architecture and why it is important. And the other one, the part of the mind map on the right. So I'm trying to get it covered. By the way, Satya had set me up with doing some ways that I could light up the parts we're done. I am failing to do that. I might succeed after a while. We point where though? Where will I have to point? On this screen? Okay, then let me figure this out. But anyway, you try that. See if you can populate, color the ones they've already discussed. So the other, oh, what has he done? Oh, he's working. Okay, all right. So if you could discuss the right side, which is electric vehicles and what their real role is relative to, well, I'm not going to feed you the thing. What the real role of electric vehicles? Okay, I'm going to feed. It's energy efficiency, okay, in transport, in my view, because EVs use 60% less energy than regular petrol engines. But if you could speak to the right side as much as you wish to, but particularly the DC architecture, which somebody had mentioned in the keynotes, and it's a favorite of mine.
It's getting late, so I'll tell you a story. I don't know how many of you were in Chennai in 2015, December, around the same time. There was huge flood. There were rains. Unfortunately, our chief minister was sleeping and nobody woke her up, and therefore the lakes, the lakes that we had, when they were overflowing, one should have opened the channels up so that water could flow to the sea, and it didn't happen in time. I don't know how many of you were here. The city was flooded for three and a half days. Three and a half days, city was fully flooded. Many homes had first floor completely submerged in water. As a result, the complete power was down. The diesel generators were also all put on the ground. They were also flooded. So therefore, there was no diesel generation also. And because the diesel generations were not on, all the cell towers also had no power. So there was no communication. I don't know how many of you were here in 2015 December when that happened. For 3.5 days, there was one home which had power. And believe it or not, it had a 125-watt solar panel on its rooftop. Very small 125 watt. It's a toy thing. But for 3.5 days, it had power. You could use your light, fan, cell phone charging, laptop charging. Of course, internet was down, but you could actually go on the rooftop, and if you stood up and took your cell phone will get connected to some remote place, and through that you could get access to it. And initially, it was actually my home. And initially, we thought it would last for 1 day because I had a very small battery, 0.5 kilowatt hour battery. So how long will it last? I was very worried that, okay, I have electricity, but next day it will go off. But what happened is that night, first night, just continued to be there, and there was no problem. Second morning, the sun came out. And as soon as the sun came out, again, my battery was charged. Every other solar system was also down. Because all solar systems also are connected to the grid. The reason my system did not go down was because the whole thing was DC. Very simple concept we came up with. That when I started working with solar, I realized that solar produces DC power and we are using AC power. So the first exercise that was done in my office room by a colleague of mine who knew much more about solar than I did, actually, we are going to put a small panel, 125 watt. So he had shown me that this solar DC has to be converted to AC. Fine. And for that, he said 15% power will get lost because you are converting small amount of solar. Well, too bad, but let's lose 15% power. But then we also wanted to put it into the battery. And battery has DC power. So we had to actually convert the AC power back to DC power. And then battery, when it is charged, is fine, it is charged. When it gives out power, it is again giving out DC power, and we had AC grid, so we had to again convert it to it. So actually, there were 3 conversions. Worst was that it was just around that time we had started putting LED bulbs, and LED bulbs were DC. So we were converting once again AC to DC. Actually, there were 4 conversions, and we're losing almost 50% of power. I kind of sort of say, what a crazy way of doing it. Why can't we put completely at DC? And only when we connect it to the grid, we convert that AC to the DC. At home, why can't we have a DC home? Well, at that time, fan was AC. But soon somebody came and told me that if you use a brushless DC motor fan, it will be much more efficient, twice as efficient as the AC powered fan, induction motor. So we went ahead and even made the brushless DC motor fan. So actually we made the complete DC. I remember when I first started doing it, many of my colleagues sort of said, well, there used to be DC. I don't know whether you have heard of this DC versus AC debate that took place in 1880. The DC proponent was Einstein. The bulb, Edison, Edison. And the AC proponent was Tesla. And for a long time, there was a debate, and it was a terrible debate. If you want to go and read that, there are actually two lobbies, two industrial lobbies fighting with each other and buying off government and buying off media, very much like what happened today. But finally, AC won because they had the transformer, and therefore they could actually transmit the power much longer distance. They could actually increase the voltage and reduce the current, and therefore reduce the losses, and therefore they could transmit. And here we are talking about going back to DC. Most of my colleagues sort of say, what are you doing? Are you taking the country backward? Are you going to take it 120 years back? I couldn't fully understand. I've seen that debate. I said, I'm using electronics is all DC. My lights are DC. My fans are becoming DC. Solar is DC. Battery is DC. Where does AC play a role? Well, we did all this. We actually did all the development because the DC development had stopped 130 years. We did everything, developed and installed it. And where did I first install it? In my office. And I remember some of my colleagues used to come in front of my room when they knew that it was converted to AC. They will peep into my room and they will run away as if there was a ghost. Because DC is a ghost. Soon, of course, people got used to it. They will come, start seeing. Say, your room doesn't look too different. I say, it doesn't have to look different. I made the bulbs exactly like a DC bulbs, exactly like AC bulb. I made my fan exactly like that, and then started using DC. Actually, I brought in almost 65%. I was consuming 1/3 the electricity for the same. It is that we actually did it. We first did it at the office. My colleagues, Dr. Bhaskar Ramurthy, our director's office. We did it at my home, and then this incident took place, and then gradually started. Still, most IIT faculty were convinced. In fact, I was able to convince all other IIT faculty, but the government was. The government said, this is taking India backward. We can't allow this. With a great difficulty, finally, I had the power minister happened to be my very close friend, Piyush Goyal. So I kind of convinced him. He didn't fully understand, but he kind of trusted me. And he had a big meeting in Delhi. Big meeting, some 50, 70 bureaucrats, 65 of them were opposing, saying, no, President Ninwala should not be allowed to install something. And I was giving the argument that it makes more sense. 2, 3 other faculty members from different IITs were supporting me, but the bureaucrats don't necessarily listen to the faculty. It is at that time Piyush Goyal was quite wise. He says, okay, fine, you people do not want it to be done. But tell me one area where you can't take electricity. So they told me Rajasthan desert next to Pakistan border. So that's a desert, and we cannot take wiring there. We cannot take AC electricity. This is what if we give IIT Madras a project to go and install every home there. So, well, that if you want to do, we have no option. And we actually went and installed 4,000. We had to take all the equipment on camel's back because there was no way you could actually reach each of them. They're distributed. One of the main reasons we could do that, one, it was far more cost effective, because we were actually using much smaller solar panel. That time solar panel was expensive. And we are using much smaller battery, because we're not wasting so much. Second, it was smaller in size to carry. Large size would have been a difference. We did this in Rajasthan desert. And after that, the Prime Minister decided to take it to every village, electricity. They found that they cannot take it up in the hills of Assam. They could not take it to Meghalaya. They couldn't take it to Jammu and Kashmir. And IIT Madras was asked to do projects in each of these and take electricity. We also went with the support of CSR to lots of villages where grid was there, but grid used to be off because there was a power shortage. It is there that we actually took the DC. Unfortunately, even though we did a lot, and we were trying to sort of put forward, saying that all the homes should become DC, all the offices should become DC, and the transmission line can be. That's what we are trying to push. That's what Vijay Raghavan supported me, and Vijay Raghavan spoke this afternoon, but I still did not get support by and large from MNRE department. So this is the story of DC. We continue to use it. I continue to use DC at my I continue to use DC at my office. Much of the research park is DC. But, and many of these rural remote homes. There has been a belief that internationally there has been a thrust towards IEEE, in fact, awarded our project as the in 2016 as the best product of the year. IEEE in the whole world for the, I think there is a clause called for the service to the humanity. But still, established things are established, and it doesn't get a sense. Even now.
We have a colleague, Kodandaraman, who can paint a few more of your areas.
Yeah. So in this mind map, our research interest is on the storage, particularly electrochemical and also ammonia synthesis. But the route we have taken for the ammonia synthesis is not mentioned here. It is like we use this renewable energy, the excess renewable energy like solar PV or wind energy, use that to produce electrochemically ammonia. So it's like, so either we store the excess energy in the battery or we convert into a chemical like ammonia, because India is one of the largest producers, something like 15 million metric tons is what we produce annually. So that is one of our interest. Besides, I'm heading the PCOE, where there are two areas which is of interest to us. One is organic photovoltaics, so under which we look at both dye-sensitized solar cells and perovskite solar cells. There are a lot of happening in the perovskite area because it's something, the efficiency is 20 plus, but we have some issues with the stability of perovskite and so on. But we kind of, our major focus is on finding organic material, because as Murgi pointed out, in the quest of introducing new technology, we should not bother our environment. That is also important, equally important. So all our interest in this center is on use of organic materials for various technologies, including battery and photovoltaics and so on. So I just made a rough estimate, like at present the generation capacity is about 700 gigawatt through the renewables. Okay, so this kind of calculation, suppose if you are interested to store about 20% of that, that means suppose 20% of this 700 gigawatt produced in the time when there is no demand from the customer, then we need to store them. So if you look for 5 hours of storage, which amounts to about 700 gigawatt hour. Okay, so if we have even a battery of like 100 watt hour per kg, this translates to about 7 million metric tons of battery weight, kg of battery, right? So that's a huge amount, especially in the coming years. There's renewables contribution going to increase. Therefore, we should find a way to utilize the renewable energy instead of going through the storage part. The storage part has to be minimum. It should not be like the order of 20% or 30%. Then probably we will run into a situation that we don't have so much material to make the battery. Okay, and even battery making is not a very clean process that also harms our environment. So we should effectively work around, we should reschedule our office hours such that we store less energy as much as lower possible. Whatever produced we should be able to use directly. This is the one point that I wanted to make. Suppose if you are out to make like some energy storage, then one way is to use organic redox molecules. Okay, there are molecules in our lab we are working on which are very stable. They are worthy for battery material. So that way, the organic is ubiquitous because it's made of carbon, hydrogen. So that's ubiquitous. Literally, there are even very complicated organic synthesis we do. So it's not that difficult to make these redox molecules. So that is one thing. The other thing is use that renewable energy in case if we have excess. Use something which goes into our industry, like the steel industry or something like ammonia production industry. So currently the ammonia industry utilizes hydrogen produced through coal gasification or natural gas sources. So that again is a polluting process. A lot of carbon dioxide is emitted. So the way we look at is we use the renewable energy and take hydrogen from water, not in the form of hydrogen, proton, right? So directly use water with the nitrogen gas from the atmosphere and use electrochemical route to convert to ammonia. So this is the idea that on which our PCOE is working on. I mean, largely it's an organic material because we don't need to worry about the kind of figure that I have showed you. It's about 160 million metric ton. If you imagine that in future we will produce about 16,000 gigawatt of power, that's roughly you need right now if you want to make the entire world electrified. I mean, use the renewable energy. Then 160 million metric tons of battery material is a huge. So that is where this organic will be a sustainable way to go. So that is the idea with which our PCOE works. Yeah, I'm done.
Okay, thank you, Brother Ram. So let's, I don't know when Satya will pull the plug on us, but in principle, we have 9 minutes, 10 minutes, he says. Okay, he went like this, but I think there were 10 there. So what I thought we might do, rather than all the other questions that I mentioned, let's pick up on hydrogen. It's a major government of India initiative, and let's get the viewpoints of the panel on many aspects of hydrogen. I mean, first of all, whether it has to be green, which means pretty much electrolysis of water, or it can be blue, which pretty much means you make syngas from wherever but capture the CO2 and do something to it. And then the question of transport and storage. It's a very small molecule. How do you transport it? Pradhan Raman just mentioned one way, it's been mentioned before, which is converting ammonia, and ammonia can be transported relatively inexpensive on pipelines. So, but I don't want to start giving answers here. So let me just pose to the panel the issue of hydrogen, let's call it. Its green, its color, and its storage, its transport, and its use. Whether any of you, yes, Arvind, why don't you go because you were first, so now, we don't have to go in a row, but go ahead.
So all the questions are pointed towards hydrogen production is one, and hydrogen storage and hydrogen transportation. And in fact, all these problems do exist. But the thing is that I'll say a quick kind of philosophy thing. So in the past, I think all our ancestors, they tried to live a sustainable life, taking the system just around them that can be regenerated. And in the last, literally 200 years, we have gone to a situation that we try to develop our comfort by finding a kind of solution or a product, whatever. And after that, that product gives a new problem. And then we run behind finding a solution for that problem. And this is how, I think this is how we keep running behind like everything. And so that's why I think I'm kind of very confident that hydrogen is a place where we use sunlight and where we use water. Of course, I'm not saying like sunlight is like all available every time and all fresh water is available every time. But still, these are two things that we can trust more on, which won't leave you a lot of waste and where you don't have to find a new set of problems at some point of time. Like the way when the plastics came up, I mean, I still like plastics quite a lot. They literally saved a lot of forest. And now we run behind saving the microplastics in the ocean. And we started burning carbon dioxide, all the hydrocarbons. They really comforted our life so much. And now we run behind carbon dioxide. And same thing, I think we run behind everything, mobile phones. And we say now computers, they say we run behind the e-waste. So we create one thing and find a problem in that, and we try to find a solution for that. And the solution will create new problem, and then we try to find one more. And I think this is a kind of like a cycle that we are running around. Although the hydrogen at the moment has a problem, I strongly believe we should really, the word sustainable is really sustainable when we go with hydrogen. I strongly believe in that. The reason is we use only water and sunlight, either wind, whatever it is. So hydrogen transportation at the moment is definitely an issue. At the moment, we know only how to transport the compressed hydrogen and liquid hydrogen. But the thing is that we have to strongly focus on hydrogen storage materials, I think, which we did not bring up at all. The hydrogen storage materials is one of the topics that like most of the US and Europe are really working on. And I think it's a high time to really focus on that business to really get hydrogen storage systems into the show. Once we try to find a solution for that, the hydrogen storage, most of the issues we're talking about, converting hydrogen to ammonia, put into Haber-Bosch process, high pressure, high temperature, and waste a lot of energy there. And now and again, you burn it again to get hydrogen out. And then you waste another set of problems there. You know, like essentially, we try to solve one problem, create another problem there itself. I know that this is going to be, I'm going to create a lot of enemies among my faculty circle by saying this. But sometimes
I think you're way ahead on that point already.
But somehow I think I kind of believe in that concept. Sometimes I think, yeah. So what I believe is that hydrogen has a problem. I'm not saying that there's no problem at all. But thing is that I'm raising that this is sustainable. Let's try to find the problems that this, whatever the sustainable life will bring, like it can bring sustainability like 50 years down the line. But let's try to work on all the problems that can potentially get away from this vicious cycle of solution, create a problem from that solution, create a problem again, and
Okay, got it. So Preeti, do you have a
Yeah.
comment on, particularly on storage, which I think I'm going to give you a hint.
No,
MOFs.
I'm going to sidestep the question and talk about an initiative that, is that all right?
That's
Because
good
it's
debating
covered.
technique. Answer the question you want to hear.
Yeah, exactly. So speaking of hydrogen, I do want to talk about a European initiative called HUGE. I'm very fond of it. I don't think, go too far, but there is hope for it. And this is regarding making hydrogen from underground coal gasification. As Vikram already mentioned, this is in situ gasification, so no mining of the coal. You conduct the reaction in the location where the coal bed is to be found. And the initiative in Europe was one of the advantages, one of the big advantages, many disadvantages, but one of the big advantages of this in situ underground coal gasification is that you can put the, there's no transport of anything that is necessary with this type of activity. You can put your plant right on location, basically. So on the surface is your whatever type of plant you want, power plant, synthesis plant, etc. And the coal from which you're getting everything for running this plant is just below the surface. So I like this idea a lot that you orient the coal gasification towards hydrogen production and use it then and there for whatever you want to use it for. So there's no, it obviates the problem of transport, which as we know, as Arvind also mentioned, is difficult. I think that strategies like this will have teeth. So this is how I'm sidestepping the question and also coloring a bit more of the mind map.
Okay, to clarify, what she's saying is underground coal gasification to produce syngas, then bring it up and shift reactor to hydrogen, correct? Okay. You have a question from the audience.
Yeah, thanks. So I'm a big believer in hydrogen, but
You are Vasu, right?
Vasu Guruswamy, but I'm not from the academic circle, so I can't be blamed for anything.
That doesn't prevent blame, by the way.
Yes, that's true. Yeah, so purely from a commercial business point of view, I hear a lot of, first of all, most of us, we are not worried whether the hydrogen is blue, green, yellow, orange, red. We actually want to know what are the technologies that work and work one step at a time, backwards. If we can do something with gray hydrogen, later on, we can convert the gray, paint it to green. The problem seems to be, the issues that are coming up are Safety, I heard about hydrogen as a bomb, okay? And I've heard of petrol bombs, and I'm sure that you know Malakoff cocktails and all kinds of things. So I'm not clear why hydrogen is a bomb. I question that more from ignorance. Maybe I could be educated. Second thing is transportation. If I'm not mistaken, it is the fuel that has the highest energy density. Am I wrong in that? Apart from, I mean, liquids or anything, but from a gas perspective, you know, compared to, let's say, NH4, CH4 or anything. So again, yeah, volumetric, yeah. So, and transportation has been repeatedly highlighted, but we also know that there are many techniques that are being used to transport fuel gases, you know, CNG and things like that, which in fact, Nikhil and me had a discussion prior to this. So why are all these seen as very special hydrogen related problems? That's my fundamental question here.
Yeah, it's seen as a hydrogen related problem only because hydrogen suddenly come up to the fore, and hydrogen is seen as a small molecule, therefore it will leak easily. So for example, in pipelines right now in Europe, they are putting in 20% cut with natural gas. They're not putting pure hydrogen. It can be done, okay? We probably want to liquefy it. But anyway, I think it is not seen, it's seen as a problem if you, and really from about Arvind's point, it's not really seen as a problem, but it is a hurdle, okay, to get it. Now, Preeti's point is make it where you want to use it. Take the mountain to Muhammad, okay? But maybe you can't always do that. So then people said, let's make ammonia. And once you make ammonia, it transports easily. And by the way, Arvind, you can regenerate the hydrogen. So I take your point. Why is it suddenly a problem? I think mainly because it's a small molecule and people think it's going to diffuse out, which is kind of right.
Yeah, because there are other transportation solutions available other than pipeline, especially considering the CapEx, OpEx play. Pipelines are not the only solution. I can quote you examples of Norway where they are transporting gas in kind of cylinders for remote places. I mean, we can discuss this, but there are other solutions available where your CapEx is not the blocking area, and also you avoid these problems of small molecules leaking through, especially joints, valves, and all these kind of things. Yeah.
I take a slightly different approach. It is true that today hydrogen, and particularly green hydrogen, is extremely expensive. And therefore, I will say it is not today's technology, but it is possible tomorrow to really bring down the cost, or at least conceivable that one can bring down the cost. Let me look at it from a different point of view. If I look at the usage, if I look at the cement production, which gives out a huge carbon dioxide, is there a better option than using hydrogen instead of coal? If I look at the iron steel production, is there a better option? It's a huge carbon dioxide emitter. I have to stop that. And is there a better option than hydrogen? If there is better option, we can look at it. If there is no better option, can we get green hydrogen to first of all become economic, number two, transportable, number three, safe? All this we have to work. As he points out, at one time, petrol was not safe, and we made it safe. So if there, similarly, if we have to use ammonia for agriculture, is there a better option than to use hydrogen? So I think hydrogen is extremely important. It is not there today. That agreed. There are lots of issues today, both cost-wise, transportation, safety. There are all these issues. But these are the challenges that we have. And we always love challenges as engineers. We solve the problems. I saw similar questions being used about lithium-ion batteries about 7-8 years back. And today, it used to be extremely expensive 10 years back. It used to be unsafe. Large batteries could not be done. And we have done all of that. So I think issue is, yes, it is not there today. Today it is extremely expensive. Particularly green hydrogen is not there, and we like to do green hydrogen if you want to move from carbon dioxide. And then we like to use it not as much for transport, because I somehow do not think it will be able to beat lithium-ion batteries for, or other solid-state batteries or other batteries for transport. But for cement, steel, ammonia, for agriculture, let's look at better option. We will probably evaluate that. Otherwise, let's go for hydrogen.
We have reached our time limit. And by the way, that was excellently put, particularly the ammonia piece. There is no ammonia without hydrogen, and there's very little fertilizer without ammonia. So that's a good way to end it. Satya is giving me the hook. We're done. Thank you very much.
I think with that, we come to the end of day one's deliberations. So look forward to having you all back tomorrow. Tomorrow's session will end a little early. We do have 2 panel sessions deliberating on renewable energy systems. That is day 2. And day 3, which is on 16th. It's an important session for us on 16th, where we are looking at hard to abate sectors such as cement, steel. And also the last session on day 3, which is 16th, is on talking about policy aspects. So we do have eminent speakers from industry who's dealt with policy, come and discuss about what needs to be done. So look forward to having you all back. Thank you.